right, in chapter 14, we're going to talk about an independent samples t-test. We did the z-test, and then we did the one sample t-test, and now we're going to do two samples. So basically, we're going to be comparing two groups to each other. Just kind of like some review, some terms here. Standard deviation, this is how much your sample, like how much scores deviate from the mean. Basically, how spread out is the data. The standard error of the mean, this is basically like our sample, how different is it from the population? That's one way to think about it. A rough measure of the average amount by which the sample mean deviates from the population mean. How far our sample is from what we believe to be the true population mean. So it's kind of also a measure of variability, except we're looking at variability of samples. You take the standard deviation of your sample and then you divide it by the square root of the sample size. And again, the SEM, that standard error of the mean, will always be smaller than the standard deviation because it's being divided by something. Confidence intervals, we talked a little bit about this last time. This is how sure we are that whatever number we're looking at is actually would fall between some different parameters, like how certain we are on it. And so usually we'll use the 95% confidence intervals. It's a range of values that we're fairly sure that the true value lies in. That's one way to put that. Last time we were talking about gas with that one sample t-test, and our 95% confidence interval was that gas mileage for those cars, the population, we think is somewhere between 40.71 and 45.29. So we're 95% certain that the true population mean is somewhere between those two numbers. The p-value, we've talked about that with correlations, regressions, the t-tests. The degree of rarity of the test results. How rare are these numbers that we've got? And so if they're really rare, we're going to consider that p-value will be really low. So the p-value will go down as it becomes more rare. And once they get to a certain point, a certain threshold, we'll call things statistically significant. So this implies that the null hypothesis is probably false. And so we talked a bit about statistical testing. We talked about hypothesis testing. And so that null hypothesis, the null hypothesis is going to be not rare. It's going to be common. Your alternative hypothesis will be the rare result. And so if you get that rare result, your p-value goes down and now it's statistically significant. Okay, and now with the independent samples t-test, again, we're going to be looking at two means. Compares the means of two independent groups to see if they are significantly different. The simplified version of that, are these two groups different? I did an example. Okay, so as far as the by hand stuff goes, we'll do a little bit. I'm going to show you a little bit of the independent samples t-test by hand. You're not going to have to do it by hand. We're probably going to be wrapping up the by hand stuff though. So we'll do another t-test next week, and we'll start getting to ANOVAs, and it's just like, it's not ever something anyone does is an ANOVA by hand. So we would always just go to SPSS. And so I do think it's, once we get into these later parts, these later chapters, it definitely benefits us to focus on the SPSS because that's what you would do in real life. An example I had, so let's say there's two different classrooms in a daycare, which again, this happens, these are examples from my life. And so the daycares that Leif's been to, there's been two different rooms. So let's say we've got those two sets of kids in those two rooms. We get their ages and we wonder, are the ages in these two different rooms, is it different? And theoretically, it probably will be, because you'll put the older kids in this room and you put the younger kids in this room. But let's just test it to see if this daycare is doing it like we would think they would do it. The null hypothesis would be the means for those two rooms. So like one room, the mean is 3.3, and in the other room, it's 4.3. And so we take those apart, and we take the first one minus the second one, we'd get like a 1, which would be pretty close to 0, maybe. So in that example, that null hypothesis would hold up. The alternative hypothesis, maybe they're 8-year-olds over here is the average, and 1-year-olds the average over here. That difference is not going to be equal to 0 because it's so big and it's a rare result, meaning that the p-value goes down, blah, blah, blah. Okay, so as that example, here's the formulas. Again, you're not going to need to know how to do this, but just for your information, this is the t-test. And so we're going to be taking the mean of group 1 minus the mean of group 2 divided by, this is the pooled standard deviation, that SP there. It's going to be times the square root of 1 divided by the n of 1 and n of 2, how many participants are in each group. This pooled standard deviation. It's just SP there, but it's actually, it equals all this part. And so it's like N1 minus the 1, that's the degrees of freedom, times its standard deviation that's been squared, plus for the second group the same thing, which is divided by both groups, the N of both groups put together minus 2. That's the degrees of freedom for both groups. So if we've got one group, it's N minus 1 to get that degrees of freedom. If we have two groups, we're going to add the participants from both groups, but then it's going to be, instead of minus 1, it's going to be minus 2, because there's going to be two numbers. You know how we have those columns, and there was that one number that could not vary. It didn't have the freedom to vary. Since we're going to have two groups, now we will have two numbers that won't be free to vary. So that's the formula. I do simplify these sometimes. So this SP, instead of making it separate, I just put this part of the formula right there, and I wrote it up by hand. And so we've got, the means minus each other, and then this pooled standard deviation times that. And so, let's just say in theory that in one room we find there's 3 kids. One's age 1, one's age 3, one's age 2. And in the second room, we've got a 4, a 5, and a 6. This is getting the standard deviation. Hopefully you remember how to do that. We would get the mean. And so it's 2 minus 2 for each one of these. And then we would add those up. The mean for this one is 5. So 4 minus 5 equals -1. Again, that degrees of freedom, if we just added this up, it's going to equal 0 every single time. That's one of the reasons why we square it, but also it means that we know, if we didn't know what this 2, we didn't know if there was a kid in there that was 2, we actually would know that, because these have to equal 0. And we've been over that in several lectures, so I know I went through that really quickly, but we went over it 3 or 4 different times now, I think, at this point. And so, we square root it because we squared all these numbers, and so we get a 1 for the standard deviation for group 1, and we get a 1 for the standard deviation of group 2. So we have a mean of 2 and a mean of 5. Standard deviation is 1 for both groups. So then we plug all of that information into these formulas. 2 minus the -5. N minus 1 is 2 times that standard deviation squared, but it's just 1, so it ends up being a 2 plus a 2 divided by, we add up both groups, the number of participants, so we had 3 in each group, that's 6 minus 2, we get a 4, so we put the 4 there, and then it's going to be times the 1 divided by the N of each group, so 1 divided by 3 plus 1 divided by 3, square root of that, because it's 0.81-ish, 0.82. We take that times this pooled standard deviation, which was 1. And so we have -3 divided by that 0.816, and we end up getting a -3.67. Again, you're not going to have to do this by hand, but I'm just kind of showing you how these work. You would get this number, and then you would go to the chart that we looked at last time. And so our degrees of freedom, again, it's going to be N1 plus N2 minus 2. So it's going to be a 4. And let's just say we're doing two-tail, 0.05, so that we look over at this 4, and it is 2.77. So if our number, it's a two-tail. So either our number, if it is bigger than 2.77, or it's smaller than -0.77, because again, we're doing two-tail. So this is like 2.7's here, -2.7's here. If we have a number above this, or a number below this, again, that's a rare number. That's a number that maybe we didn't expect because it's so different from each other. So anyways, if our number is above or below a 2.7, then it is significant. And again, ours was. We had a -3.67, so this is a rare result, and it is going to be significant, statistically significant. In fact, let's see, if we looked over, it would still be, I would put p less than 0.05 because it does go in between this 2.7 and, if we were looking at the 0.01 level, 4.6. Degrees of freedom, N1 plus N2 minus 2 equals 4, so that 2.7677. Okay, we talked about confidence intervals last time too. And so this is like that range where we think that the true number lies. I think at this point, let's run it in SPSS real quick. To double check a couple things. Let's see here. So we got our classroom. How you enter this in SPSS? So you would enter the ages. I put age 2. I don't know why I called that, but a 1, a 3, and a 2, and a 4, and a 5, and a 6. Those are our ages. Since it's two groups, we need to put them in there by groups. And so for room 1, I put a 1, a 1, and a 1. And for room 2, a 2, a 2, and a 2. So these 3 people are in room 2, and these 3 kids are in room 1. We'll need that to be able to do the statistical test here. So I'm going to click Analyze, Compare Means, and now we're going to do Independent Samples t-test. We did 1 sample last time. This time it's independent samples. We'll click that. Let me reset it. So our classroom is going to be our grouping variable. Age is the test variable, the thing that we're trying to test to see if they're different. So we'll put age there. How we group them is going to be that grouping variable. So we're going to put classroom, we're going to move it over here, and then you do have to define the groups. Usually it's just easier just to call them group 1 and group 2, and then all you have to do is click that define and click continue because it already puts a 1 and a 2 in there. It's kind of an extra step that's almost unneeded, but yeah. If you would called your group something else, like if I had called them a 0 and a 1, I would need to go in there and put 0 and 1 instead of 1 and 2. So save yourself some time, just put 1 and 2. When I first started, I did 0 and 1 because that's what made sense to me, but it's just easier if you put 1 and 2 for the groups in a independent samples t-test. Click OK. We'll get our results. So in a 3 in each one, exactly. The mean was a 2 and a 5, perfect. Standard deviation is a 1 and 1, just like what we got with the handwritten one. Go down here, and it is significant. We were doing a two-tail, so it's 0.02. Again, I said it was going to be in between 0.05 and 0.01, and it is 0.02. Mean difference of 3, our standard error. Okay, so we have our confidence intervals here. You can do those by hand, but I wanted to show them here. Our mean difference is 3. What these confidence intervals are telling us is that if we were to look at if we kept getting these samples over and over and over to find out what the true difference from a population standpoint would be for those two, and it's going to be somewhere between a negative 5.2 and a negative 7.3, which is pretty big. You know, if you had an actual daycare and there were 5 years, you know, if you had 10-year-olds here and 5-year-olds here, that would be a pretty big difference. So, and like I mentioned last time, see, these are both negatives. So it means it is way slanted this way. So yes, we did get a mean difference in our samples of -3, and we think with 95% certainty that if we just kept doing it over and over and over with different samples, that it would be somewhere between -5 and a -7.3. On Cohen's d, we haven't talked about this before, but this is an effect estimate, standardized effect estimate, so Cohen's d. And so, yeah, we're talking about effect size, and we're describing it by the observed mean difference in standard deviation units. Usually, like a 0.2 is considered a small Cohen's d, a 0.5 is considered a medium, and a 0.8 is considered large. You just take the mean difference between the two groups divided by the standard deviation, and so that's what that looks like. We had a 5 and we had a 2, and it's divided by our squared, the pooled standard deviation of 1 square root, so it gives us a 3, which is huge. You know, if we had a 0.8 is large and we get a 3, that's really big. When we're talking about these effect sizes, basically what we're saying is that these two samples, they're different. It's like, how different are they? And a 0.2, it's like, yeah, they're a little bit different. A 0.5, it's like, yeah, they're different. 0.8, pretty different. And then when we get to like a 3, okay, these two samples are so far apart, they are quite different. There was a pretty good image here in the book of this. So like if you have a Cohen's d of 0, the two samples are almost exactly the same. And so they're going to be overlapping. And so if you take them as standard distributions, they're just right on top of each other. If you get a Cohen's d of 0.2, now those two standard distributions, now they have moved over a little bit. And so there's quite a bit of overlap, but there's a little bit that's kind of sticking off on the sides. So 0.5, that gets even larger, 0.8, and then like ours was a 3.0, very little overlap between these two samples because they're so different. And so yeah, a big Cohen's d means that your samples are quite a bit different. All right, there was another example in the textbook. They talked about EPO. I don't know if you know what this is. It's blood doping. There was a bunch of bicyclists that got caught doing this a number of years ago. It's basically like, I don't remember exactly how it works, but they like take your blood out and run it through something and then put it back into you, and it makes your endurance go up. Sounds dangerous, but yeah, there was quite a few people do that. MMA fighters, there's been some caught doing that too. So it increased EPO increases endurance. And so there's a lot of data out there to support that. So they ran an experiment in theory where they took a group of depressed people and half of them they gave EPO and half of them they didn't. And they wanted to see if it would, help with their endurance. It could maybe help with their depression. So we have two groups, group 1 and group 2. The textbook, they put the experimental group as group 1 and then the control group as group 2, which I guess is fine. I always did it the other way though. For me, I always had the control group as group 1 and the experimental group as group 2. It doesn't matter, but what does matter is that you know which is which. So however, if you start running experiments, make sure to keep consistent which group is control and which group is experiment. Then they test them on their endurance. And so like one person got a 3, one person got a 13, etc. Our hypothesis, our alternative hypothesis, is going to be that the group that takes the EPO is going to be significantly higher in endurance than the group that doesn't. And so it's not that it's not equal to 0, it's that it is going to be greater than 0, the difference between those two groups. Meaning, some of you, if you think through it, this means it's going to be a one-tail test. We're only going to be looking at if it's above a certain threshold, because we have a theoretical background for that. The EPO does increase endurance. So the idea that we would give EPO to depressed people and then cause their endurance to go down, possible, but not likely. We're going to set up to check out where our critical T is. We get our degrees of freedom, N1 plus N2 minus 2. And so if we go back here, there's 12 participants. So 6 plus 6 minus 2, we get 10. We are doing a one tail. Let's go ahead and do it at 0.05. And so our critical T value, the T value that we need to meet, is a 1.8. If we get above a 1.8-ish, then we're going to have a significant finding at that 0.05 level. In the textbook, if you want to see another way of doing it by hand, you can do that. Feel free. There's two different tables. I put them in the PowerPoint so you can see how they figure this up. It does look like they get a T value of 2.6, so it's going to meet that threshold. We, though, are going to do it in SPSS. And so click Analyze, Compare Means, Independent Samples T-Test. We'll reset. We're going to put endurance is our test variable. And then, let me double check this. Yes. Group 2 is going to be our grouping variable. You'll have to, again, define those group variables, 1 and 2. They're already put in that way, so it's good. Click OK. In group 1, the experimental group, they had a mean of 11. The control group had a mean of 6. There's your standard deviations. This is what we're interested in. T value, 2.15. And so we did do that one-sided, one-tailed. So we do get a significant finding. P is at 0.03, so P less than 0.05. If we'd done a two-tail, it would not have been. So again, you got to figure that out before you do the test. If we had decided that we'd run a two-tail, then we run it where it's like it's not significant, then you're like, we thought it was going to be one tail the entire time. It's not right. Don't do that. And then we get our confidence intervals. Okay, so our mean difference between the groups, one group's 11, one group is 6. That means our mean difference is 5, obviously. We are 95% certain that the difference, we kept running these samples over and over and over, that the difference between those is going to be either somewhere between a negative 1.7 and a 10. So that's pretty huge. We're 95% certain that's in this huge bullseye. Generally speaking, those confidence intervals, the more people you run, the smaller they'll get, and then you'll really start to hone in on what the difference would be. This is a pretty huge difference. This is basically saying that one group could be one group is 6 and the other group is 16. So that's a pretty big difference. But again, it's because we do have fairly small sample size. And then, we can get our Cohen's D here too, that we talked about just a little bit ago. And this is a 1.2. And again, 0.8 is a pretty large effect size. Getting a 1.2 is pretty big. Okay, this is how we would write that up. The endurance scores for the EPO group or experimental group, we list their mean, we list their standard deviation. And the control group, mean, standard deviation, differed significantly. this difference of 5, and then we list our 95% confidence intervals. What's significant? Give our T, that degrees of freedom, our T stat, which that's right, P less than 0.05, and our Cohen's D. So we're going to list all those things. And I did make a little chart, or like not a chart, but I color coded it. I've had students in the past that were into this color coding stuff. So I should have underlined the mean though. Whoops. So mean 11, mean 6. Our standard deviation comes from there. Standard deviation comes from there. Our 95% confidence intervals come from right here, the green ones. Our T comes from, here's the degrees of freedom, the 10. That 2.16 comes from right here. And then our Cohen's D comes from right down here, that 1.2. And yes, so it can be claimed with 95% confidence that the interval between negative 0.17 and 10.17 includes the true effect size, which is the true difference between the population means for endurance scores. Another way to put that. You don't have to write it up like that. And so, yeah, this gives you their means with their standard errors. And so, yeah, you'll notice that even if we include their errors, that they don't overlap. And generally, that's going to suggest that those two groups are very, very different and that you're going to have a significant finding. If they were pretty close and there was overlap there, might not be. That's just kind of a rule of thumb. I did list another study, so let's go ahead and run that one too. I think my thought was on this, I just created it, is that we have a group that's taking an anti-anxiety drug, and then we measure on their measurements of anxiety after they've taken the drug or after they have it. We're going to analyze, compare means, independent samples t-test, reset this. We are going to move, let me double check, group to here, 1 and 2, and then we'll move, I believe it's anxiety, the first one. We'll move it up here. Now before we run it, we want to decide if we're going to do one tail or two tail. Either way would be appropriate because, you run the anxiety study. I think I would do a two tail, and this is why. If it's a brand new drug and you don't know what the effects are going to be, it's possible that you give them this anti-anxiety drug and it actually causes anxiety to go up because it's not a well-formulated drug. And so that's probably why you'd want to run a two-tail. If you ran a few studies and you're getting significant findings, that your drug is decreasing anxiety, then you might want to switch over to a one-tail. Okay, so I ran a study. We had an N of 12 in each group. Mean of 3. The mean is their anxiety scores. So we got a 3. And for group 2, we have a 5.16. Okay, and so now I go down here, we get a T. It's a 4.7. So you probably already know that is going to be significant. And that's actually significant at the one tail or two tail, and it's less than 0.001. So I'll write that up as P less than 0.001. It does list our mean difference. And then we get our confidence intervals. So our mean difference is a 2.1. We are 95% certain that the mean difference, we kept running it over and over, is somewhere between a 3.1 and a 1.2. So that's pretty narrowed in. We got our 2.1 and a 3 and a 1. Those are pretty close together. So we got pretty good confidence intervals on that. Hopefully have a pretty good effect size too. Let's see. Yeah, we got a Cohen's D of 1.9, which is really big. Meaning that these two populations, these two distributions are not really overlapping that much. And so, yeah, this is how we'd write that up. Again, the mean, standard deviations, our confidence intervals, our T statistic, the P, and the D. So you can find all of these in the output. Just a couple other terms I want to talk about real quick. A meta-analysis is where you take a bunch of studies and you put them together. It's just like a statistical analysis for a bunch of studies. So let's say that we got that new drug. We do 100 drug studies. We publish these 100 drug studies, and then we can do a meta-analysis where we take all of the data from those 100 articles and condense it down into one to say, okay, we have so much compelling evidence that, this is really happening. Or, you might run a meta-analysis and it's like, oh, the results are kind of weak when you add them all together. And one reason they might be weak that you might not be aware of is because a lot of studies that don't have significant findings don't get published. And they call this the file drawer effect. If you run a study, you want to get a significant finding so that you can publish it and so you can move forward with your career. it's hard to publish things that don't have significant findings, because like, why do we want to publish? That's what some people would think. Why would we want to publish something that doesn't have an actual finding? But not finding something is actually a finding. And it's like, it's for science to progress. We need to know when we're not finding what we're supposed to find or what we expect to find. We need to know that so other people don't run it. And so it also gives us like replications. People don't publish replications, but they probably should, because then we would find out a lot of people aren't being able to replicate other people's work. And in the last couple decades, at least 10 years, we have found this replication crisis, because a bunch of people started to try to replicate studies and it's not happening. And now they are starting to publish these. There's actually one group of researchers that has really honed in on several areas in like social psych that have not been replicating well. So just something to think about. All right, I think that's all for chapter 14. If you have any questions, we can definitely talk about it during class. Thank you for listening.